I want to start off by thanking Seth for having me talk to all of you today. I'm very excited actually to talk about question answering from SQuAD to industrial search. Just to give a little bit of background about myself, as Seth mentioned, I'm a deep learning engineer at Deepset based here in Berlin. We're very interested in a lot of the deep learning technologies in NLP, and especially interested in language models and question answering and what they can do to help build industrial search systems. Yeah, I'm getting to do a lot of very interesting deep learning projects with Deepset here. And yeah, I have a background in computational linguistics where I did my master's at Stanford. And prior to that, I was working on languages, especially classical languages in Cambridge. So yeah, just to set the scene for you guys, Deepset, we kind of see ourselves in this position bringing the latest research into industry. So right now in research, if anyone is familiar with what's happening in NLP, I'm sure they've noticed that there's quite a surge in work in looking into transfer learning, into language models, and also into question answering. Yeah, as I already mentioned the SQuAD dataset, which is the Stanford question answering dataset. And we're going to see how this can form sort of the basis of a lot of different other bigger systems. We're very much interested at Deepset in using these new research technologies to create industrial neural search. So driven by these advancements in question answering, we're working on Haystack, which is an open source, open domain question answering framework, helping you answer your queries on your own big set of documents. Yeah, so the core of this is open source, and we also develop enterprise features on top of that to create production-ready systems. And we've already been working a lot in the industry with a lot of different partners, but all who have this same information need to really be able to get the best out of their unstructured text data. So you can see just a couple there, including Siemens and Airbus, who we've been working with. So I kind of want to start off by talking about a kind of search which I'm sure everyone's quite familiar with in terms of web search. So everyone uses it very, very regularly. And maybe it's kind of hard in using it day to day to really track sort of the advancements that have occurred. But it definitely has improved. Google has obviously been working on it very heavily. And one thing that I want to point out here is that Google started off much more in this kind of conventional search style of ranking different web pages. So you might want some sort of specific information like the address of the Eiffel Tower here. But what it used to just return was a page which might contain that information, which you would have to dig a little bit deeper into to read and to get the answer for. Now, with modern NLP-based methods, it's actually possible to build systems which are much more accurate than that now. If you have the same query, if you want to find out the address of the Eiffel Tower, you see that Google actually returns you not just page, but really the exact string span, or in this case, the address, which answers your question. So yeah, just want to point out here that we are talking now about queries in natural language and very granular answers, very fine-tuned answers, which are really honing in on what the information need is. We at Deepset are working a lot on these sorts of technologies, and we see quite a gap between what has been happening in web search and what is currently available in enterprise search situations. And for this reason, we've been working very hard on this demo here, which I will switch over to right now. Seth, are you able to see this right now?
Yes, it's good.
Okay, great.
By the way, if you could start the video, that would be good.
Oh, as in of my own, me personally. Sure, I can do that. Here we are.
That's good.
Great. So yeah, I just want to give you a sense of what's possible with this kind of technology. So in this demo, we have a large corpus of documents. They are actually annual reports and earning calls from NVIDIA. And for example, we might be interested in asking questions about revenue. Maybe we're interested specifically in how high was the revenue in 2019. And in the back end, BERT, which is the language model, which I'll be talking about more specifically, is doing its work, reading through a lot of documents, and is able to here not just give us a relevant document, such as the fourth quarter report from 2019, but you can see highlighted in green here, actually, the very specific information that we've been requesting. I can just try one more quick example for you. Maybe something a little bit more open-ended. How
Branden, when you show your example, you need to change your sharing to the web browser or whatever it is you're using.
Is it currently just, can you only see my slides at the moment?
I see your desktop right now.
Oh, I see, okay. Let me do this again.
You actually might actually quickly go back to what you were showing before first.
Sure, let me do that. Can you see my browser at the moment?
See your desktop. You need to share your browser specifically.
Yeah. And how about now? Is that any better?
No, sorry, you're seeing my photo.
Okay. Oh, no, but this is, if I switch the tab, how about now?
That's good. I see NVIDIA
Great.
or report.
Exactly. So maybe let's go through the first example again. I assume that we missed that. The question that I typed in was, what is the year in 2019? So yeah, Bert is reading through the stack of documents and will return a list of documents which might contain the answer. These seem pretty relevant to me. We're talking about Q4 reports from 2019. And in green here is that exact answer to the question that we just posed. We can ask something a little bit more open-ended, like how is the outlook?
Branden, we had a request. Can you zoom in, please? Can you enlarge?
Yes, sure, of course. So how is the outlook? Here we have it.
That's good.
And yeah, we have also, again, a set of documents returned and sections highlighted, which this model thinks is relevant to this query. So for example, I've highlighted the section which says we expect cryptocurrency-related revenue to be negligible going forward, which is actually quite relevant in this case. We have a relevance score here to give a sense of what the model thinks of it. We also see a line here, we expect competition to increase from both existing competitors and new market entrants with products that may be less costly than ours. So yeah, we see a lot of potential here, actually. We really think that this is the future of how we're going to be doing search on an enterprise level, not just by keywords, not just with Control F, but really with natural language and with systems which understand language, read through it, and make some sort of sense of how sentences are put together and how it's used in practice. So at this point, I want to come back to my slides here. And I want to talk about the different components that we need to build this kind of a system. And I'm going to talk about it in a couple of sections. I want to talk firstly about language models, which are really what underpins this language understanding component of these systems. I want to talk about question answering, which is a very popular NLP task, which is very integral to this. And then I want to talk about scaling. How do we get from extracting an answer from just a paragraph to extracting an answer from a large set of documents? So let's get started here. Language models, what are they? What do they do? In the most basic sense, a language model is something which understands the distribution of words, and through that is able to guess words in certain positions. It has a very good understanding, a very good representation for what it sees, and is able to get a sense of what a sentence means. So here, if we had a sentence like the fox something's across the street, a good language model should be able to assign high probabilities to words like runs, trots, or walks. Why does it function like this? Well, a language model needs to be able to build a good representation of the context of these words like the fox and across the street to make these good guesses. And practically speaking, it does this by representing them as vectors. But it needs to build good vectors that allows it to make good guesses in these missing spots. Effective language models should be able to learn from massive unlabeled data sets. It really needs to have seen a lot of language to really understand how language functions, the rules of it, the meaning of words, compositionality of it. And on a practical level, language models, as I said, are the foundation of many modern NLP systems. And we're going to talk a little bit about just how flexible they are in these coming slides. So I kind of want to show what modern NLP workflow looks like when you're using deep learning models. And here, what you might do is start off with a language model architecture. Might be BERT, might be AccelNet, but something which can learn. And the first step you might want to take is to give it a large corpus of unlabeled text. Practically speaking, this is often scraped websites or Wikipedia dumps. And by reading through all this text, the language model learns over time, and as I said, gets a good understanding of the distribution of words in the language, gets a good understanding of what words really mean. Once you have this trained language model, you might have another task in mind. And for this specific task, you have a layer on top called the prediction head, which is tailored towards it. You might be doing document classification, you might be doing named entity recognition, you might be doing question answering. In this case, we might be doing question answering. We have a question answering data set. And when we pass it into the language model converts these tokens, the text, into a set of vectors represented by these green bars here. These green bars are consumed by the prediction head, which then finally spits out an answer appropriate to the task, such as the question answering answers to your questions. And so through this process, you also train the prediction head. And through all this, it's these two components, the prediction head and the language model, which form your fully trained question answering system. I want to give a little bit of a brief timeline of how we've gotten to where we are now with the language models. Some of you might be familiar with very early models, early vector space models, such as GloVe or Word2Vec. These are uncontextualized vector space models, which are very efficient. They were very effective when they first came out. And actually, for certain cases now, still potentially the choice to go for. This is a very lightweight, but often very effective method to go for. They're very powerful, but they have one very clear drawback, which is that their representations are uncontextualized. So to give you a sense of what this means, you might have a sentence which is talking about an apple or apple, just generally. And in some cases, you might be talking about apple, the fruit, in which case you would have one vector for it. But in some cases, you might actually be talking about Apple, the company. And in this uncontextualized model, we're using GloVe and Word2Vec. Both these cases are represented by the one vector. And you can see already that that's very suboptimal. In these two contexts, Apple has very, very different meaning. And that's why there was a push towards contextualized models, such as Elmo and ULMFit. And these were a big improvement upon these uncontextualized style. And these models were initially built using this LSTM architecture. It's a recurrent neural network architecture, which reads in one token at a time. LSTMs, saw a lot of use in NLP and still do. But they have a couple of quite significant drawbacks too. One of them is that they struggle a lot with long sequences. When they're reading one token at a time, eventually they kind of forget what came maybe 100 tokens before, 200 tokens before. They kind of have an amount of memory that fades as you go. The other issue with LSTMs is that with our current hardware, they're not the most efficient architecture, in that it's very, very hard to parallelize over a GPU. You need to take one step before you can perform the next step. And that gives some limitation to how quickly they can process text. Fast forward to what we have now. The latest generation of language models are contextualized transformer models. This transformer architecture is something that you'll find in a whole range of models, like BERT, like XLNet, like all the BERT variants, such as Roberta and Albert, which we'll talk a little bit more about later on. But this is the state of the art at the moment. These are the most performant models, and these are the ones which really get the most out of advances in hardware design. So yeah, I want to talk about just what kind of models there are out there, and why I keep talking about this BERT model. BERT is a really, really important one in the context history of language models, and it's a really, really big step up when it first came out. It was the first really effectively shifted to this transformer style of language modeling. It's trained on, the original version is trained on a corpus of about 13 gigabytes of data, made up of wiki articles and a book corpus. And it's trained using two tasks, masked language modeling task and the next sentence prediction task. And as we saw before, this kind of architecture is very flexible and it can be used for lots of different tasks. As I said, document classification, NER. This BERT model is the foundational language understanding. It's not task specific. You perform some kind of fine tuning on a specific task in order to turn this BERT model into something that is a little bit more tailored to a more practical case of some sort. But if you're reading papers now, and there are lots of language model papers coming out every month, you'll often still see BERT as the baseline model, just because it was so influential. It was such a big step up, and it's just, such an effective design. BERT spawned a lot of other kinds of models. A lot of people wanted to make improvements upon BERT. And one of these, for example, is SpanBERT, which wanted to push by changing the masked language modeling task a little bit. Instead of just masking single tokens, it masks out whole spans and creates a much harder task, and they report some performance gains there. There's the Roberta model, which is actually quite popular right now and quite effective too. It is, in essence, very, very similar to BERT, but with lots of minor tweaks. They add some more data, they train for longer, they remove the next sentence prediction head, and they have a larger batch size. And they managed to improve upon BERT that way. Albert is another variant that also came out from Google. BERT originally came from a team from Google, and Albert is an improvement from Google, which really sought to shrink down the number of parameters in the model through a set of different enhancements. And there are a lot of teams looking to actually make BERT even more efficient. And one of these, which I think is really, really cool, really, really interesting, is DistillBERT. It uses this distillation technique, also known as a teacher-student learning method, whereby you start with a large, fully trained model, like BERT, and then you have a much smaller student network, might just be a smaller version of BERT, which tries to copy what the larger BERT does. And it copies not just the output predictions the BERT makes, that the teacher makes, but it also tries to copy the confidence that the larger model has over the range of available class labels. And through that, we actually end up with models which are significantly smaller, but actually retain a lot of the performance of the larger model. That was just a couple of them. There are so many models out there now, and so many really awesome, really cool new techniques coming out. Here is a very brief overview of it. But yeah, I think just by seeing how many models there are there, I find it actually a very exciting time right now to be in the field of NLP and seeing what's coming next, how people are trying to push forward the field. So what can we do with these language models? Well, one of these tasks is question answering, as I mentioned. And at this point, I want to show a quick demo as to what question answering is. So here, I am on a demo page that we created that is going to leverage an English BERT model trained for question answering. And here we might put in a company description paragraph. This comes from Wikipedia. And we might want to ask it a question like, what are the divisions of Airbus? This is from an article about Airbus. And if we run this, once again, we'll get highlighted the appropriate answer: commercial aircraft, defense and space, and helicopters. We could also try something like where is Airbus located? And we can see, yeah, Airbus's corporate headquarters is located in Leiden, Netherlands. And what I really wanted to stress here is that there's not any kind of rule that is being implemented behind the scene here. This system really actually reads whatever is typed into this question. You can type in any kind of question. It has to try to make some sort of semantic sense of it and apply that to the passage to identify an answer span. So going back to the slides. Yes. So to kind of describe this task a little bit more specifically, question answering is actually a very broad field, and we're talking about quite a specific subset of question answering called extractive question answering. And it works like just we saw just now. You have a question, you might be asking, what is Berlin? And you might have a text passage, another paragraph from Wikipedia, and you want to ask that question, and it's the job of the system to highlight an answer. In this case, the largest city of Germany. There are quite a lot of challenges to this kind of task. So to really perform well at this, a model has to really be able to understand what the text it's reading is and what the question being posed is, and really act upon both these things. It may have seen the passage before, but it might not have had it paired with a question. The system has to really be able to act on the fly and understand the information we need. The other thing is that there are a very large set of potential predictions. If we have a passage here, any span of text could potentially be an answer to a question somewhere, and this model has to be able to pick out just the right one. And in practical terms, text that the model reads often can be quite long. Here is quite a limited example. We have just a paragraph from Wikipedia, but to really match information needs of people, the system might have to be reading through large documents or even stacks of documents. There is the standard approach nowadays is to train a model that can identify the start and the end of an answer span. And we're going to see a little bit more in detail what that actually is. But yes, it's no surprise that language models form the basis of these systems. We get a language model like BERT, we fine-tune it on labeled question-answer pairs, and we found that this actually works quite effectively. We get a system which is able to tell you this is the start and end of the answer you're looking for. And I mentioned already a little bit about SQuAD. So as I said, SQuAD is a very, very popular question answering data set. It's almost a default in the field of question answering. It presents one Wikipedia paragraph and pairs it with various questions. And yeah, human annotators have highlighted the answers to those questions. It's a very useful data set to get your model to learn how to perform question answering. So I want to show a little bit more of a practical example of what's going on behind the scenes here. So let's say we have this same example here. We have the question, what is Berlin? And then we have the text from the document, which is this Wikipedia paragraph. They're in yellow and blue respectively. We pass this into the language model BERT, and BERT returns these contextualized word vectors. There's one word vector for each token that comes in. These vectors are then passed on to the question answering head. And it's the job of the question answering head to return the start and end token, which means that the system can extract the largest city of Germany as its predicted answer. How does it actually choose this beginning and end? Well, when the prediction head is given this set of word vectors, there's a feed forward layer which is applied to each one of these vectors, which spits out two outputs. It spits out start logic and an end logic. When it's confident that this position is the start of the span, the start logic will have a high value. When it's confident that it's the end of the span, the end logic will have a high value. This feed forward component will iterate over each position until we can get this stacked up set of start and end logics. And then you pick the best span out of here. So as you can see, as represented by the red, these positions have very high values and will be taken as the prediction by the prediction head. So why are we talking about question answering now? Now is actually a particularly good time to be working with question answering because transformer-based models have significantly boosted the accuracy of that is possible on these question answering tasks. And it's actually made it really practical to implement these in industrial situations. So on the right here, we see a graph of actually the performance, the state-of-the-art performance on the SQuAD dataset over time. And it might be hard to see the numbers, but I just want to focus in on one feature of this, which is the big surge in performance in the middle of this graph. And that happened around November 2018. And that is attributed to the release of BERT, the first really successful transformer-based language model. The performance increased hugely overnight. And since BERT, there have been lots and lots of incremental improvements such that now we're actually at a point where these systems outdo the human benchmark. There's a lot of momentum in research right now working on this task of question answering as well. There are a lot of new data sets coming out which are really trying to push this question answering task in different directions. They're trying to make it more difficult, more challenging, and they're trying to build systems which will be more robust and be able to answer more information needs. So there's a big push towards getting systems which are able to synthesize information from different parts of text. For example, systems that can read one sentence from early in a document, see something much later in the document, and be able to combine these pieces of information to present a relevant answer. As we saw before, there are a lot of new model architectures coming out as well, and these are showing lots of improvements, not just in question answering, in a whole range of tasks, but the benefits of these better architectures is definitely being passed on to question answering. There's also a lot of work getting question answering and language models to operate on not just English, but a whole set of languages. XLM Roberto is actually a very nice case of this. It's a single model that can handle 100 languages at once, and it actually shows very, very competitive performance compared to even a lot of the single language models. We think it's also a very interesting space to be in right now because we see this need in industry to have state-of-the-art search systems. And we think this technology, this interest is really going to drive a lot of development in building the systems that people need in workplace environments. So we really see that there's a large growing number of information workers who have complex queries and who would really benefit from having a tool that is more powerful than simple keyword search. And we also see, as I mentioned, that there's a big gap between the possibilities in web search and what there is in enterprise search. And so we in DeepSet have really seen that this technology can really help in trying to narrow that gap. We're really, really driven to see what we can build to help people answer their questions through their own documents. And here I just want to give a quick overview of some of the data sets out there. So I've talked a lot about SQuAD. We have SQuAD version 1, which became SQuAD version 2 when they added a lot of no answer or negative examples. For example, in SQuAD version 2, you can now have a question that cannot be answered by the passage which is at hand. And in that situation, the model is meant to say that, exactly, to say that, okay, the question that you posed can't be answered by what I have. I don't know how to answer it at this point. There are other data sets out there that are interested in working with differences. For example, there's visual QA, which actually operates on images. You have a question, which you might be asking about an image. There are some data sets which work on tabular data. There is a set down here, which work on reasoning and synthesis. As I mentioned, it's really trying to push together different bits of information from different sources and trying to make some sense of that. There are a lot of data sets which have translated SQuAD into different languages or use the same methodology to create non-English SQuADs. There are sets which are designed to have lots of different languages together. So they do question answering, but they have parallel examples in, for example, Japanese and Arabic. There is open domain question answering, which is interested in answering questions not from just one document, but by looking at a whole corpus of documents. And there is new answer types which are popping up. So natural questions here gives the model certain examples where it's expected to give back a yes or a no as an answer. Did this event happen in this year? The model sometimes, in that situation, cannot actually highlight a span which would answer that kind of a question. An effective system would have to respond with a yes or a no. One thing that I want to point out is that SQuAD is a very, very effective data set, and it's created some really, really cool models which are able to do some very incredible things. But there are certain limitations to SQuAD. And one that was picked up on relatively early stems from the fact that the people who wrote the questions for SQuAD did it by reading one of these Wikipedia documents and coming up with a question. The issue with this is that often the questions that these writers come up with include a lot of the same keywords that exist in that document. And with this kind of lexical similarity between question and document, we actually get a much easier task. It really doesn't leverage the full power of language models, modern language models, which are very capable of understanding synonymy or very flexible enough to deal with different wordings, different phrasings. So you can see by these little I symbols, these I've just highlighted are data sets which have made it a very strong point of generating questions in a very different way, such that the question writer does not see the document that the answer is contained in, and therefore is not wording or yeah. And so these tasks are actually much trickier and really push models to their limits. Has a lot of potential, and we see the potential in it when we can scale it to an open domain kind of setting. This is something that really reflects the information needs of workers much better. And this would be something like having a question like, what is Berlin? But trying to find the answer to this, not just in the Berlin Wikipedia page, but perhaps in a large collection of documents. There are a lot of challenges to this. I'm going to switch a little bit of the terminology here. What I've been calling these question answering systems in the context of open domain QA are called readers. That's the system that kind of reads very closely each sentence, each line. As it stands now, transformer models are limited in the input length that they can process at a time. And this is a challenge that has a lot of researchers very interested in, which a lot of people are working on right now. But currently, this is definitely a limitation. It's hard to ingest that much data and process it completely. There's definitely a need for speed in any system which is going to be answering questions. And this only gets harder when we're talking about larger collections of documents. And one other thing I want to point out is that these reader models, these question answering models, when they read through lots of different documents, might find not just one candidate answer, but a whole set of candidate answers scattered all around the place. And then in these situations, we need to have some kind of logic that tells the model which one to pick. How do you weigh up these answers that are scattered across different documents? And I want to stress that it's not always just an answer that is a span. As we saw before, we have no answers, we have yes and no answers. How do you weigh these against each other? So one popular approach is something known as the retriever-reader pipeline. And it looks something like this. On the left, You start off with your big store of all your documents. You pass this to a retriever, which is a much more lightweight system that actually filters down to just your top K documents. It's this which is passed on to your reader, which are these deep learning based models that we were talking about. And it's this reader which has the job of extracting the exact span. In some of our experiments, we've been working with readers and retrievers. And in a setting where we had about 7.5 thousand documents from the natural questions development dataset, we were using a Roberta base model and a Tesla V100. If we were trying to make a query with just the reader, we're talking about over 3 hours for a single query. But with this two-stage approach, when we have the retriever in there as well, we can reduce this number down to just about 1 to 2 seconds, actually. And so, yeah, there's a certain trade-off here in that in trying to speed this up, we can't pass all our documents to the reader. But as I'm going to talk about in the next couple of slides, there are a lot of ways that we see improvements coming along. So yeah, I just want to talk a little bit about a couple of different approaches to readers and retrievers right now, and yeah, give a sense of sort of what level of performance we're at the moment. So if we had something like a perfect retriever, something which always returned the right document, we would expect a retriever top 20 recall to be perfect, to be 100. And using our best reader models right now, this number is taken from the leaderboard of the natural questions task. We could expect something like a 51% in top 1 exact match for the extracted span. So in a set of documents, we expect this kind of a model to be able to 51% of the time extract exactly that answer span that answers the question that is being put in. And yeah, here we have an overview, which is a very established baseline that's used for the retriever. It's a variant of TF-IDF, which I think a lot of you would be familiar in a lot of ways, such that frequency doesn't scale quite as heavily as in TF-IDF, for example. There are a couple of other techniques here, such as latent retrieval, the ICT, and also the Realm paper, which just came out this year. The one that I kind of want to talk a little bit about is dense passage retrieval, which uses a dual encoder architecture. The reason I want to talk about this is because I kind of talked a little bit earlier as though retrievers, as though readers are always deep learning models and the retrievers are from some other architecture altogether. But dense passage retrieval is something that might shake this up. Dense passage retrieval is showing a lot of promise, and it is actually using deep learning for the retrieval part of it as well. And so how it works is that we have two encoders. We have two based encoders, and we have one for the question and one for the passage. Passage and the question into a shared embedding space, such that when you have the dot product of question embedding, the passage answers the question, or at least the passage contains the answer to the question. One of the coolest things about this paper is their success comes from. So the idea behind it is that for each question, you want to train it on one positive passage and a few negative passages, some passages which just don't contain the answer to that question. They do something very smart called negative sampling. Oh, sorry, something called in-batch negatives, whereby in the batch, the positive passage for one question is used as a negative passage for another question. And by doing this, they gain a very effective, a very efficient way of training. And yeah, they managed to get some very nice results out of this. One other step that they took was that they combined multiple QA data sets to augment their data. And they showed quite convincingly that actually this gives them quite a lot of improvement. So if you really want to use this at inference time, the idea then is that you have a big corpus of documents and you pre-compute embeddings for these documents. You index them to some systems such as Vice by Facebook, and then you want to retrieve case neighbors when you have a query. You have a query, you embed it, and you retrieve the document embeddings which are nearest to it. And as I mentioned, we have deepset on our own open domain question answering system. And it's called Haystack. It's open source, and yeah, you can try it out already. Here's the link for it, and that's the GitHub there. But we have a little snippet of the code, a couple of sections here, and how show sort of how those concepts that I've been talking about are implemented. To start, you would have a document store. Maybe I'll zoom in just a touch. You can see highlighted here, the document is the component which holds all your documents. We have the retriever component, which is this first filtering step where you pick just a subset of the most relevant documents to your query. You have a reader, which is this deep learning based question answering system, which is really going to extract that bit of text that will answer your query. We put these together through an object known as the finder, and we call it to get a prediction. So yeah. Yeah, I hope you guys can try that out sometime. Actually, it's quite fun to work with, and we have a nice little demo for Thrones fans, where we have preloaded a set of Game of Thrones articles like who is Arya Stark's father and so on. It does actually surprisingly well on those. But to wrap up kind of what I've been talking about, yeah, we see right now that transformer models have enabled extractive QA. We've seen some really big performance gains in there. And we see that this can really drive the development of industrial search applications. Even though these are more in an open domain sphere, we see that there's potential to scale up extractive QA into open domain. We have these components known as the retrievers, which in QA, they filter out the search space such that the reader doesn't have to read through your whole document store, but just a subset. And yeah, we want you to play around with this kind of technology. We think that we found it really fun to work with, and with it too. You can try it through Haystack. And to give just a little kind of roadmap of what we see ahead coming, we see that there are going to be a lot of improvements. We see that there are going to be new data formats coming out. We see that there'll be support for tables and figures and images. We see that there will be new retrieval technologies coming out, like the dense passage retrieval. We see that people will be working on more reasoning and synthesis. And we see that they'll actually, I think that in the future, we'll also see extractive QA, but it's all kind of in this sphere. And we see that these systems are only going to get better and better at answering information needs of people when they're looking through their own stack of large documents. So yeah, thank you very much for listening. I hope that was helpful and interesting. If you ever want to get in touch, here are some links to our Twitter and LinkedIn handles, and also to the GitHub repositories that we've been working on. Thank you.
Thanks very much, Branden. We have quite a set of questions. I'll make the remark that further down the horizon from the slide that you've shown, I'm waiting for argumentation. In other words, not just answering questions, but putting forward arguments that are essentially a series of answers that move people to a certain position. So if you want to take a look at the Q&A, we have, looks like 12 questions there. Some of them you've answered in the course of your talk. I can read them to you, or you can read them yourself, read them out loud, that is. Which is your preference?
Yeah. ones would you think? Yeah.
Okay, let's start at the top. We have one that I think you've largely answered already. Stephen McInerney, can you comment on not English SQuAD type data sets? I think you've done that, but do you have any further comment? As for the target language other than English, what are relative pros and cons of taking an answer from an English model and translating it versus direct query on a model in ELP? I think you've largely answered that, but do you want to say anything more?
Yeah. I do actually. That's actually a really interesting area that we've been working a lot on at DeepSet. In a blog article that talks about lots of different types, lots of different attempts. And I would love to share a link to that perhaps after this talk or through this chat thread. But what I want to really focus in that is that there are two big approaches. There's the machine translated style. Let's start with English SQuAD and try to maintain the alignment. And there's this method which actually tries to replicate the methodology of SQuAD. Let's get human, like people in Mechanical Turk or human translators to create a parallel SQuAD. And what's been quite clear through all this literature is that machine translation by itself is not enough to create an effective SQuAD equivalent data set in another language. By contrast, these human methods have proven to be quite successful. They've been able to create models which actually, like, they've been able to create a data set, for example, in French, which is not as big as SQuAD, but can still train a model to get a lot of the performance of SQuAD. But one last thing I want to add is that hybrid approaches as well, methods where teams have gotten human translators or animators to create, say, an Arabic version first, and then to add on top of the translated Arabic SQuAD examples. And in some of these cases, we also see a performance boost by adding machine translation. But really, the bottom line is nothing beats human annotations.
All right. Let's take I have two questions from Harish Ramani. One is, how do we evaluate the models? What's the metric? And the second is, if he has his own data set, what's the first thing he needs to do so that he can do question answering on it? Does he need to start with named entity recognition? How do you evaluate models and how do you get started?
How do you evaluate models and how do you get started? Sure. Yeah, to evaluate how well a model is doing question answering, there are two metrics that I use generally. There is the F1 span overlap. So essentially, let's say, I hope you can see in my webcam here. Let's say here is that answer that we're talking about. This is Berlin is the largest city in Germany. And your model predicts something that's like here. So there's some overlap, but it doesn't get it exactly. There's an F1 metric to kind of calculate some precision and some recall to say, okay, this answer kind of got some of it, but not all of it. You're not going to get a full 1 out of 1 or for this, but you'll get some small number. So that's the more granular metric that's used to measure how good these models are at extractive QA specifically. The other one there is exact match. So in this case, your model only scores 1 out of 1 on a certain sample if you really have exactly the same start and end. So those are the two evaluation methods. How would I get started in it? NER actually is not really necessary to build a good QA system. A lot of the times, the answers that we're talking about are actually not named entities at all. Sometimes the answer that you need is maybe a whole sentence or even a whole paragraph. And so NER might be kind of good like markers for what are relevant topics in this area, but QA, you don't really need it. As a starting point, I would point to SQuAD. As I said, SQuAD has become really popular. We've been able to get very good performance on it. It's really the archetypal extractive QA dataset. But once again, I would give the caveat that it's essentially solved. It's a slightly limited task, and we're seeing this next generation of datasets coming out, which are much more challenging, much harder, and which are really pushing systems to the edge.
Okay. I have two people with their hands raised, Eric Agri and Vineet Kumar. I'm going to call on them after the next answer. So I also have two questions in here from Paul Trezsotko, which I think you've mostly answered just a moment ago when you answered about metrics. What is relevance based on and search performance versus for Q&A versus traditional TF-IDF search? Anything further to say about metrics and relevance?
Yeah, sure. Just to give a sense of how that, you might be talking about that relevance number that we saw in the demos and how the model knows how confident it is with a given prediction. There are a couple of things that go into that. One of these is these logits that we were talking about. We saw those dots which represent each position, and when it's red, means that it's a high value, means that the model's confident. Based on that, we can calculate how confident it is of that span. There's also, yeah, on the document level, depending on your architecture and depending on what kind of retriever you use, the retriever might also be able to return different confidences that a certain document is relevant to your query. Could you remind me what the second part was?
Search performance versus traditional TF-IDF search.
Search performance versus traditional TF-IDF. Yeah, yeah. TF-IDF has been like a very. It really has been very effective for how simple it is, and I see it still being used. In some cases, we have systems which still have a fusion of deep learning methods mixed with TF-IDF. What I would say is that TF-IDF has a very clear drawback, which is that it relies very heavily on lexical overlap. It really relies on a query having the same terms as the document. If there is not that kind of overlap, TF-IDF will really struggle. If you use a synonym, if you use, just a word that means something similar but not the same, TF-IDF can't really pick up on this. By contrast, these deep learning models are much more robust to synonymy. They're really projecting words and their meanings into an embedding space so that words with similar meanings will be represented in very similar ways. On the other hand, deep learning models are going to struggle in cases where it's dealing with words that it's never seen before. TF-IDF can in a very shallow way deal with this. If it is dealing with a proper name or some just entity or word that it's never seen before, TF-IDF doesn't really care too much what it means. It's just interested in whether it exists in both the question and the document that you're searching through.
Vineet Kumar, I am promoting you to panelist so that you can ask your question directly if you're still there. While we're waiting for you to unmute, then I will just remark that, yeah, TF-IDF has been around for several decades. I've seen presentations in recent weeks that refer to keyword and context. Quick indexing, that's been around since the late 1950s, and we're still finding a lot of relevance in it. Vineet, do you want to answer your question directly?
Hi, Vineet.
Vineet? That doesn't seem to be working, so let's go back to the questions that we have entered here. We have Melanie Beck. There's a lot of excitement over Distilbert's smaller footprint and faster interface inference time. However, it does lose a considerate amount of performance on the SQuAD datasets, particularly on SQuAD 2.0. What's your take on this model, that is on Distilbert?
I think that I see Distilbert in just a movement of research that is very, very important to the field. These models that we're talking about, these deep learning models, are big, and their size is often one of the challenges of getting them working in production settings. Distilbert is one really, really cool approach to this, but it's not the only one. And there are things such as people are pruning away weights which aren't learning. There are new architectures like Albert, which are trying to reduce the number of parameters. And there are this is where I think the most promising developments are. There are a lot of new transformer architectures, which are going to work on much longer, larger spans and do this much more effectively and efficiently. So yeah, it is a concern right now that that Distilbert isn't enough to kind of get us to deploy from GPUs to CPUs. But I think we're really like there's just a lot of work going on out there, and we're going to see some very different models coming out to really make these fast enough to work. Yeah, hopefully even just on a CPU, just on your local laptop.
Okay. I think we'll probably keep going for maybe another 10 minutes based on the questions that we have.
Sure.
We have a question from Frank He. I want to ask advice on how to deal with dialogue transcript QA models, since the corpus has longer text length, around 5,000, and text structures are different than a traditional document. So that is dialogue transcript QA.
Mm-hmm. That's a very interesting one. Yeah, so what I'll stress is that most of the data sets that I mentioned today, the documents are more something along the lines like Wikipedia documents. And so when you're talking about context in that case, you might be talking about the context of what came in a paragraph before, what came in the sentence before. But in dialogue, you have a very different interaction of text when you have two separate agents. If I'm to be completely honest, this isn't an area that I'm very familiar with. I haven't worked a lot with a lot of dialogue text. But I think that there is definitely a slice of research out there which is working on things in this sort of domain. If I'm not mistaken, I can't quite remember the name of this paper, but a team in Stanford were interested in sort of having sort of an iterative QA system, which was kind of given an information need, given a query, and it would sort of return back questions that would try to like refine the search space and so on. Conversation between that system and someone who's kind of has an information query. So a different style, but yeah, there's definitely work in this field. I just have to say that I'm not super familiar with it.
Yeah, certainly a lot of dialogue does involve trying to refine and often rephrase the questions that are being asked. And that was the basis of a search engine from 15 or more years ago, Ask Jeeves. The initial release of Ask Jeeves was trying to take an iterative approach to get better relevance on the question. So just a very quick one. Are you going to provide the slides for us? I'll post that, and the other Meetup hosts can post that. Is that okay?
Yeah, definitely.
Okay. We have a question from Avinash Vyas. Can you please share a pointer to new QA models that can answer a question using separate part of the paragraph as opposed to the start and end span of the answer? If you can interpret that question.
Sorry, could you say that again?
The phrasing's a little difficult. QA models that can answer a question using separate parts of a paragraph as opposed to the start and end span of the answer.
Yeah, sure. So one that I would point to first is natural questions. Natural questions has annotations which are not just a single span. Sometimes you might, ask something like, who was in Led Zeppelin? And maybe these entities don't come up very neatly in just a single string. Maybe they're scattered across a couple of different paragraphs. And in natural questions, you do have these, what we call multi-span answers. There is another data set, and I have to I don't remember if it's exactly this one. I believe it is Hotpot QA, or maybe Trivia QA. It's one of the ones in this cluster here, between those, which has not just like an answer, but also like supporting facts which lead to that answer. And so building the systems that are built for that, really have to be able to deal with this synthesis. And I can see that there's a lot of potential to train a system there, which answers with either multiple spans or even potentially provides some kind of reasoning for why it picked a certain span.
Yeah, well, talking about the facts or whatever that lead to an answer, that's the essence of argumentation, whether it's argument mining or argument production. We have a question about training BERT language models on specific data corpus, such as medical jargon.
Sure. Yes, there's definitely a lot of interest in creating BERTs, which are.
I should say that some of the participants put forward BioBERT, SciBERT, DocBERT. I don't personally
Exactly.
know about that, but yeah, go ahead.
Yeah, exactly. Yeah, there's definitely a lot of demand for that kind of those kinds of models. What I would say is that there's a bit of a trade-off here. So one of the challenges in training a model from scratch is that you need a large amount of text. At a minimum, I would say in the range of like 10 gigabytes of just raw text. In doing so, that's the only way to really get a well-trained language model that is going to perform well. There is a method known as domain adaptation, which can, after reading this sort of first set of text, you can kind of use it to sort of fine-tune your model towards being familiar with, medical data or scientific data or legal data. This fine-tuning step, is really just kind of getting your model accustomed to new jargon, to new style, to a new domain. There is one trade-off with this, which is that when you do this, the vocabulary of the model is already somewhat fixed. There are ways you can kind of add some tokens in, but the motivation behind some of these other models, I believe like BioBERT, is that you want to train it from the very beginning just on medical text so that it is very focused on this kind of text and particularly good at it, has a really well adapted vocabulary for it. But yeah, ultimately, I think it comes really down to how much data do you have and are you going to be able to train an effective model? 10 gigabytes is really a minimum. We're talking in like the hundreds of gigabytes for some of the latest models.
All right. And what about integrating multiple models, ensembling that is, and scoring mechanisms if you do integrate multiple models via an ensemble method?
I'm wondering whether this is specifically for QA of, I assume this is talking about question answering now. Is this from a different?
Ensemble methods have been around in many different contexts for a while. So
yep.
Yeah, since this is a talk about Q&A related specifically to that.
Sure. Yeah, definitely. I think that in almost every task that I've seen in NLP, like in leaderboards, top results almost always come from these ensembled methods. And you can really quite reliably get gains in performance through this. Yeah, like I'm all for it. And I think that if you're really trying to push through state of the art, this is a very, very common method. Obviously, it's going to be a lot more intensive in terms of compute, in terms of methods that you use. But yeah, if you can afford to do it, by all means, go for it.
Okay. We had two questions from Nikki Aurora about question answering for student answers in university examinations, for, where's his other one, for grading assignments, final exams, stuff like that. I will interject here also that this was articulated as one of the so-called grand challenges for AI by some people I follow like 10 or more years ago, is doing this sort of evaluation. But anyway, applications for grading assignments, final exams, academic settings?
Yeah, that's a very interesting one. It's a very interesting one.
So let me, you seem not to really be on top. I actually know people, for instance, at the Educational Testing Service here in the United States, they administer the statistical aptitude test, the SAT exam and other exams. And they are working very hard on this because they would like to be able to automate the scoring of the responses, the essay type responses that are given as part of their tests. So work's definitely going on.
Yeah, I definitely agree. And I think that to characterize what these models are good and not good at, I would say that they definitely offer what I would call like a much more fine reading of text than we've ever had before. Word vectors were good at kind of just telling you what a word sort of means and kind of grouping together similar words. Now we get these models which actually read a sentence and compose it and really kind of say, okay, this verb plus that noun has this sort of gist to it. there are still some very big limitations to what they're capable of doing. I think that that we're not really at a point yet where we can really like have a very good representation of the reasoning, perhaps, or the style, or the eloquence. Actually, at least the reasoning and sort of how do I put this? The world knowledge and the conceptual understanding of a student. I think that this kind of technology can still be used for a lot of different things. I think there's a lot of potential in actually style analysis. But in an educational sphere, I kind of think that I would like to see this technology used as a tool for students to be able to get to what they need in order to study effectively, to learn effectively, and yeah, to do well in their courses.
Let's do two more. I'm going to group together three responses to the discussion a few moments ago about TF-IDF and so on. We have Yasser Martinez. Have you seen examples of non-TF-IDF systems? For instance, pure retrieval on production. Stephen McInerney says, surely the middle ground between TF-IDF and DL is connecting to a knowledge base. That's a different wrinkle here. And Yuri Schlachter, to follow up on TF-IDF, what's a good way to incorporate OOV? I don't know what that is actually.
Out of vocabulary words.
Yeah, okay. Into vector and language model based methods. So non-TF-IDF systems, yeah.
Yeah. Yeah, in the little summary that I showed before, I think what I was trying to convey there is that we're actually very excited about these dense passage retrievals. These embedding methods are really the most robust systems we have right now. And the issue with getting them into the retriever is, how do you train one that's good enough, that is fast enough, that can be used at scale? And dense passage retrieval is one of the first papers which really show that this is a possibility. You just need to, what they really showed was that they found a very good way to train it effectively and show the performance there. The idea there is that, as I said, you just have an embedding for every document in your corpus. And this is really just the most kind of fine-grained retrieval we can have right now. Knowledge bases, I have to admit, are really not my strong suit. And I know that there are a lot of knowledge-based approaches out there. But we really see that there's going to be a lot more development as well in these dense retrieval methods. And we find that really, really promising. I just want to make a quick comment on the outer vocabulary. So these deep learning models, these transformer style ones, mostly use some kind of variant of things like word piece tokenizers, which split up a word into kind of component parts. If a word has not been seen by this tokenizer, it will revert in lots of small chunks. Maybe respectfully would be kind of broken up into respectfully or something like that. But if it's seen enough words, it will, if it's seen a word enough times, it will have that word as just a single token, as a full token. So the hope is that basically these models have seen components of outer vocabulary words enough that it can kind of make a good guess as to what it means. But in some sense, I've been a little bit roundabout about this, but in some sense, no word is really treated like out of vocabulary by a deep learning model. It just is forced to kind of make a good guess as to what that word means based on certain parts of it. Sorry, that's a very, I'm trying to capture a lot of information about how tokenizers work there, but with these newer methods, out of vocabulary is not as big, is not really as crushing an issue as it was in, say, word vectors.
Okay, so we'll take one final question, and that relates to your job, which I thought could be an interesting way to close. Sushant Singh, does your job involve developing products with respect to research papers in accordance with industry needs? And how is that different from people working on purely NLP research? So about what you do.
Yeah, sure. We're really doing a mix of these things. So I'm actually currently working on a paper about trying to, we've been training a lot of German language models and getting models which are really pushing forward performance on named entity recognition and document classification. We've been working a lot with the Electra model, which came out just this year, and is a very cool twist on BERT and has shown to be much more efficient at training. So there is a component of my work which is very research related. I'm always trying to read whatever new is coming up, and it's very much in the DNA of DeepSet to to be following what developments there are in QA, in language modeling, in open domain QA, in transformer architectures, and so on. But at the same time, we're building this open source software. We're working on projects with people in industry, and we always have an eye to making software that people will actually be using. That's really something that is essential to us.